Okay, welcome to the Week 3 lecture for Astronomy 390, aka Astronomy 124. This week we're going to learn about CCDs, and I'll answer other questions you may have in class, but feel free to contact me. Okay, so what is a CCD detector? CCD stands for Charge Coupled Device. This is basically the equivalent of a digital camera that we put on the back of our telescope. All right, I'm recording this, so it's still getting used to the WebEx system here. Okay, so basically they're digital cameras that we put on the back of our telescope with some key differences that we're going to talk about. CCDs are what we use as the detection device, generally in optical and infrared astronomy, coupling photons into electrons, which we call charges. So coupling charges, charge coupled device, CCD. The history of CCDs was that they were actually invented at Bell Labs in 1969, 50 years ago. And they were intended as a memory storage device before their image detection capabilities were found. And what that literally means is they were measuring current coming from these devices, and they realized the current changed depending on whether or not the lights were on or off. And so they realized that they had actually, instead of inventing a new type of computer memory, they had actually invented something that was sensitive to recording the amounts of light. Within a decade, they were first used for astronomy, and we'll talk about later why they're so important for astronomy. But the first use of a CCD, a digital camera, in astronomy actually dates back to 1976 in Arizona, and followed one more year later, used in 1977 on the 200-inch Palomar telescope in California, which at the time was the biggest telescope in the world. So clearly CCDs were very important to astronomy. We got them on sky right away on the biggest telescopes in the world. And we'll talk about in a little bit what's so special about them. One thing I do want to say is that for those of you that enjoy taking selfies, you have astronomers in the military to thank for the existence of all of our digital cameras on all of our cell phones today. Basically, as you know, cell phones haven't had cameras they've only had cameras for about, digital cameras first started coming to the market in the late 1990s, so 20 years after they were available on astronomical telescopes. Now, the story goes that the military has spy satellites, and back in the day, spy satellites used to use camera film to take images. And the satellites would literally, after all the film had been exposed, literally they would eject the film canisters, which would then survive re-entry back to the Earth. And then the U.S. military would have to travel around the world to recover these film canisters containing spy footage and develop them and to learn their intelligence about other parts of the world. And this was, as you can imagine, a very costly and risky maneuver. In addition, it would take weeks or months between when the data was collected and when the intelligence would be available. On the other hand, the military realized that this invention of the digital camera would have incredible benefits because they could take an image, convert it to an electrical signal, and then convert that into a radio transmission. And so CCDs became very important for the spy satellite industry because it allowed them to instantaneously, or nearly instantaneously, transmit the data down from spy satellites to the ground, no longer needing to physically drop film. And of course, this revolutionized the spy satellite industry, and the march was on to make digital cameras in greater quantities with more pixels. The very first digital cameras had very few pixels in the visible. In fact, the first infrared digital cameras only had a single pixel, which, by the way, is the basis behind the technology of heat-seeking missiles. Heat-seeking missiles basically have infrared cameras on the front of them, and that's how they determine which direction to point based upon where the heat is located. And those originally were single pixel heat sensors as well, usually 4 pixels, a quad cell we'd call them. So in any event, astronomers in the military literally spent billions of dollars, mostly the military spent the money, and astronomers reaped a lot of the benefits by making digital cameras better. More pixels, less noise properties, faster readout times, things of that nature, until one day in the 1990s, they became cheap enough to put in high-end digital cameras. And of course, it cost several $1,000s. And of course, the rest is history, right? Today, cell phones have digital cameras that are incredibly cheap to manufacture. Lenses made out of plastic most of the time, and these CCDs are ubiquitous all over, and have greatly impacted our modern society. And I like telling this story because it's a great example of how investment in fundamental research, work done at Bell Labs, the use of astronomical CCDs on telescopes for 2 decades before they became a viable commercial product, I think is an important story to tell about how sometimes you don't know exactly what the payoff is going to be for our society and our economy. This is a great example of a digital camera, something that was for pure research and military purposes for 2 decades. And then it became something that's now completely transformed our society. Okay, so what is a CCD detector? Let's dive into the details of how these things work. A good analogy is the eyeball, right? Your eyeball has a lens, and at the back is the retina with rods and cones. The CCD is the retina. It's the rods and cones at the back of your eye. It's sensors. The CCD detector, each sensor is a pixel. It's a pixel arranged in a grid. It could be square or rectangular. The pixels can be square or rectangular as well, in a single large-scale integrated circuit. Basically, a CCD is a computer chip. It's made out of the same material. It's a substrate of silicon. The front side consists of a large number of regularly arranged computer gates and channels layered on a substrate of silicon. And here's just a diagram showing different, on the bottom right here, showing different pieces where the actual pixels are located here in the middle, as well as some bond pads for connecting wires to read out the electronics. And then there's some special pieces here called a serial register, which I'll show you a little bit more on later. So the idea of a CCD is we want to count the number of photons that fall in each pixel to get a measurement of the brightness of objects in the sky. So just like one puts, the focus of your eye is on your retina, and I'm wearing glasses today because apparently it's no longer the case for my eyeballs. Nonetheless, the CCD is located at the focus of a telescope. Okay, so the image, so what happens is these photons hit and come to a focus from a star on a particular pixel, and the photon gets absorbed and then kicks out an electron from a silicon atom. And that moving electron is a current. That free electron, something called a valence band, which we'll come to in a second, is something that we can count. We can count electrons. We can measure current. We have voltmeters for that. And so the image of the sky is recorded as a pattern of electric charge counts. We literally count electrons. Here's another diagram showing what this is like. And this is a diagram of the type of CCD that you might have in your cell phone. And so you have your pixels in the middle, and then it does something to read it out. So basically, you take an exposure, and you wait a certain amount of time to generate electrons in each pixel. And then you literally shift them out. You literally shift them out of each pixel over to this special set of pixels called a serial CCD shift register, which is like a really fast, deep set of pixels. And then all the pixels shift by one. It's called the bucket brigade. I have an animation to show you that later. And then basically it goes out to something called the output amplifier here. So first the pixels come down, and then once one row of pixels has moved into this bottom serial shift register, they all move out to the left here in the diagram to the output amplifier. And the output amplifier is where it applies something called a gain, where the voltage is multiplied. Again, that's a computer chip, a computer circuit. And then we have some clock controls on the right there. And then we measure that voltage, and that basically one pixel at a time, and it literally tells us the number of electrons that were in that pixel, which, as it turns out, which is why it's special to astronomy, is proportional to the number of photons that hit that pixel. Now, there is a key difference between digital cameras in your cell phone and digital cameras that we use in astronomy. You know, going back to this diagram, you'll notice the zoom of this individual pixel here. There's 2 green, 1 blue, and 1 red component. Now, each phone CCD pixel is actually a group of 2 by 2 monochrome pixels with color filters on top, and these are manufactured en masse today. These are automatically combined in software phones to make color images. CCDs, the pixels themselves, do not record color information or the energy of the photon. So they use filters to only let a certain color through, red, green, and blue, to the pixels below them. And then so they count how many red photons there are, how many green photons there are, and how many blue photons there are. And then in software, these are combined artificially to make a color image that represents approximately what your eyes would see. And this is why oftentimes the pictures you took don't necessarily match the colors that you see. There's another problem too. Your eyes have large dynamic range and CCDs do not. That's why CCDs suck at doing dark light images on cell phones. In any event, in astronomy, on your cell phone, you get color images every time you take an image with a lot of post-processing. A huge amount of software goes into processing images these days in cell phones. But in astronomy, we want the raw data. And so there are no color filters on top of each individual pixel in the CCD. We take monochromatic images instead. So they generally have a large single filter over the entire thing that we can switch out. And so on our campus telescope, for example, we have 7 different filters that we can use to collect images at specific wavelengths, and we'll learn about those next week or in the coming weeks. Additionally, a big difference between digital cell phone cameras and astronomy cameras is that it works a lot better if our CCD pixels are bigger. They're more sensitive to collecting more photons. On your cell phone, you're taking pictures of bright things during the daytime usually, and there's plenty of photons around. But in astronomy, we're taking pictures of things that are very faint, the stars that are fainter than our eyes can see. And so we tend to have bigger pixels, and thus the digital camera CCD sensors themselves can be much bigger. In fact, the Kepler Space Telescope with its 100 megapixel camera was huge. I mean, the size of that digital camera was quite, physically large. I think it's something like about this big, big compared to, say, a cell phone digital camera with 12 megapixels. It'd be smaller, just a few millimeters across. So the sizes of pixels in digital cameras and cell phones are much smaller, generally on the order of a couple microns. Whereas the CCD pixel sizes on our campus telescope, for example, are 9 microns, which is actually in and of itself a little small, but oftentimes we actually do want bigger pixels. Okay, so what does a pixel look like? So now let's look at a single pixel inside a digital camera. You might call it a MOS gate. It's a fancy word for a miniature capacitor. So you have to have an electrical connection, and that's the top layer. And you can have light coming in from the top or light coming from the bottom. That refers to whether it's front illuminated if it's coming in through the top, or back illuminated if the light is coming in from the bottom. There are different reasons to have different orientations of your CCD. And then they have multiple layers. They have something called a polysilicon gate. They have a silicon dioxide layer, and then they have the layer of silicon. And the silicon is where these electrons are sitting that can be freed up by the electron light, by the light coming in and freeing up electrons. And I'll talk about that in a little bit on this next slide. So what happens when a photon hits a pixel? Well, a photon is absorbed by the valence band of silicon semiconductor. So that's this bottom layer here. And it allows an electron to jump into the conduction band, which is going to be in this, I think in the silicon dioxide layer. Actually, I don't actually recall. And it changes energy. The electron gains energy by absorbing the photon, and it goes from what's called the valence band to the conduction band. So the valence band is where it's trapped in a silicon atom. The conduction band is now in the metal layer. This is where the electron can now move freely within the pixel. It's not bound to an atom. It's kind of like ionization to some extent, if you're familiar with that concept. Now, the way silicon works is that the energy difference required to kick an electron out of the atom, and this is just by pure material science chance that this works. There are other materials that do similar things that have different cases, but for the case of silicon, this doped silicon that's in a single pixel, it requires that the photon have an energy of at least 1.26 electron volts, and then that can cause the electron to jump from the valence band to conduction band, leaving a hole moving away from the positive gate. So the positive gate is this thing up at the top here. And so the electron will go up, the hole will stay down associated with the silicon atom, and then this is now the electrons are up in here and they can be free to move. So the pixels have a term I just want to at least mention, which is the full well capacity, and that's the maximum number of electrons that can be stored in the conduction band before the electrons and holes combine. So if you know a little bit about positive and negative charges, of course, right, the silicon atom minus the electron now has a positive charge, right? Those two charges are going to attract each other. And if you have enough charges in both layers attracting each other, electrons will start jumping back down and filling those holes in again, those missing electrons. And that's something called saturation. And we'll use that term, saturation of a pixel. There's another reason you could saturate due to the digitization that happens in the output amplifier stage of reading out a CCD. But long story short, what do pixels do? The light hits the silicon atom with a certain amount of efficiency that frees an electron into the conduction band, the metal layer of the pixel, and then we can trap those electrons with voltages until we're ready to count them. So, to read the pixels, how do we count electrons in each bin? To read the pixels, the voltage are varied so that the electrons are shifted by columns and rows in a readout register, and that's what I showed you earlier. The number of electrons are then converted to voltages plus what's called a small bias offset as well as an amplification. This voltage, which is it is quantized due to quantum mechanics, right? It's individual electrons moving. But nonetheless, this voltage gets digitized into a number with something called an analog to digital converter. Now, before we had digital computers, we actually had analog computers. And you can still build analog circuits. I'm sure there's some physics labs you can take here where you build analog circuits, learn about things called op amps and all sorts of wonderful electronics. But modern age is digital computers, so we have to convert the current, the voltage that's fluctuating in each individual pixel into a number. And so that's done with the A to D converter. And that literally converts it to bits, ones and zeros. And so the maximum value of an A to D converter is defined by the number of bits that the device can count. Now, in our example, our campus telescope camera has a 16-bit A to D converter. That means it can count between 0 and 65,535, which is 2 to the 16th minus 1, because there's 16 bits. 2 to the power 16 is 65,536. Some digital cameras have fewer bits. 4096 is a 12-bit A to D converter, and so on. Generally speaking, this is another case where you get saturation. So we generally design the thickness of the silicon layer in a digital camera's pixel to have enough electrons to free up so that you can get at least 65,000 of them without having the electrons jump back down after the photons have hit. So you can actually also saturate a pixel if you have more than 65,535 electrons in that pixel. And that's simply because the A to D converter can't count that high. You would need to add more bits, and adding more bits means more wires, and that makes it more expensive. There are, as far as I'm aware, no scientific digital cameras with more than 16-bit counting ability. Now, this is different from color. You may have heard about like true depth and all this other stuff, like 24-bit color, 32-bit color. Well, remember that we take monochrome images. So if you were to imagine having a 16-bit monochrome digital camera, then you arrange it with color filters on each. You have 16 bits of red, 16 bits of green, 16 bits of blue, and then your full color image in that case would actually be 48-bit color, which is enormous. It's 65, 536 to the third power number of colors. I don't actually know what that is off the top of my head. But in any event, 65,535 counts, or electrons being counted, is a pretty typical number in astronomical detectors. And that's just how the digital cameras of astronomy are made today. That may change in the future. So looking physically about how individual pixels are drawn, I don't know what's going on with that image, but that's fine. That's really strange. Every third electrode is connected, so let's go back here. So every third electrode is connected together to make a pixel. So if this is a pixel, this is an individual pixel drawn in this red box. There are electrodes, 3 per pixel. So this is what is an electrode? It's a freaking wire. Okay, it's just a wire. And then perpendicular to that, you have gaps in the silicon to define columns. So rows are defined by wires, and then you have gaps in the silicon, so-called channel stops. And so the channel stops prevent electrons from going left and right. And then the wires are going to be used to control electrons going up and down. So looking at the side view, we have p-doped silicon at the bottom. That is the corresponding to this bottom layer here. And then let's make sure I got that right. Yep. And then we have N-type silicon and insulating oxide on the top. So these are basically the same layers as we were looking at over here. And then finally, how do we use this? So here's the trick on how digital cameras are read out. They apply voltages or current to the wires that cause there to be voltage potentials inside the silicon. And if we were to imagine looking at the pixels from the side, now here are these same 3 wires corresponding to 1 pixel, 3 more wires corresponding to a second pixel in the upper right here. We apply currents to each of these wires, or hold them at particular voltages, so that there's a high voltage here, a high voltage here, and a low voltage here in the conduction band in the silicon dioxide layer, and that's where the free electrons are going to collect below this second wire, based upon how these wires have voltages applied to them. And similarly over here. So we need 3 wires per pixel for a very specific reason. We need 3 wires per pixel to move the electrons, to move them from one pixel to the next, so that we can count them at the edge of the digital camera. So this consists of a 4-step process that happens like with a computer clock, going at frequencies on the order of millions of times per second. And so every computer clock step occurs. And basically what they do is they change the voltages on each of these gates or wires so that we make the voltage bin bigger, so that the electrons spread out between the 2 wires. And then we close up the old one that had a low voltage, so that we move the charges from one piece of the silicon dioxide layer to the next, so on and so on. So this is a way that we move charges from one pixel to the next. It actually takes, well, this actually doesn't get it all the way. This is actually a 6-step process to move it from across 3 wires, so from one pixel to the next. And that's how we transfer charges from one pixel to the other across a digital camera set of pixels, all the way to the edge. And then we take all those edge ones out and put them through the amplifier to count them. It's quite a sophisticated computer chip-driven process, and it works remarkably well. We talk about things called charge transfer efficiency. How well are we able to move the charges from pixel to pixel? Is there any latency? That kind of stuff. When you really dive into the details. The voltages that come out are very low, so they often have to be amplified by an on-chip amplifier. And of course, we have the A to D converter, as I mentioned earlier. One thing I want to mention then is that what we report the number as is not number of photons, nor number of electrons, but oftentimes something called ADUs, or data units, or sorry, that's the analog digital converter. So we do call it ADUs occasionally. We also call it counts. And so the analogy of how this is read out, this is just done with voltages and moving charges around, but a good analogy of how this is done is something called the bucket brigade. So you can imagine that a good analogy for a photon is that of a rain bucket. A rain bucket collects rain. Pixels are basically photon buckets. They collect photons that get converted into electrons, and then using and applying voltages, we shift those buckets of electrons out to this special serial register, which is a single row or column of pixels, depending on how you're orienting yourself here. And so we move those electrons into this other bucket, and then very fast, we then dump those buckets, again, using that same process, many steps that now run at a much higher rate, out into this output amplifier. And so we count the number of electrons in every pixel one at a time, which is kind of nuts if you think about it, but that's literally what digital cameras do. There are some digital cameras that have multiple output amplifiers and have multiple registers, as they're called. And so modern near-infrared digital cameras, for example, can often have 16 or 32 of these special rows and amplifiers to count pixels faster. Otherwise, it would take too long. So, for example, a modern 16 megapixel camera, you could spend a minute counting all those for a near-infrared camera, which is made out of a slightly different material, totally different material, actually. But nonetheless, it can take a while to count all of these. So oftentimes, modern digital cameras have multiple copies of these output amplifiers to speed the process up. And again, it's usually some power of 2. There's 16 of them, or 32 of them, or occasionally more. So now we're at the point where we know a little bit more about why digital cameras are important to astronomy. They let us count photons, but it goes beyond that. They're very efficient. So digital cameras, we can quantify the fraction of the percentage of incident photons hitting each individual pixel. They're actually converted into electrons, something that we can measure, a measurable output. I'll make sure the audio is coming through here. Yeah. So the first important property of digital cameras, which is why they became so rapidly adopted in astronomy, is that their quantum efficiency, the fraction of photons that get converted into electrons, is incredibly high. On average, 70%. So 70% of the photons that hit generate electrons that go from the valence to the conduction band, to which we can eventually count when we read out those pixels. And nothing like that had ever existed before 1969. Previously, astronomers primarily used two things: photomultiplier tubes. You can think of a photomultiplier tube as like a single pixel counter. But those weren't that efficient either. Maybe 15% of visible wavelength photons would be converted into electrons. So it wasn't, you couldn't see things as faint with it, to mention the fact that it was only a single pixel. And before that, we used to use something called photographic plates, which are basically glass with a photoemulsion on them that would be exposed exactly like the old camera films that used to be used. And maybe some of you have seen those in your lifetimes. But generally speaking, Film was also incredibly inefficient. Even for photographic plates, typical quantum efficiencies of 1%, maybe 1 out of every 100 photons, produced something that we could measure in the film for astronomical applications. In fact, film and eye have similar sensitivities. So the CCDs really represented a revolution in efficiency. We could just have a huge advance in sensitivity, a factor of 70 times more sensitive than photographic plates were for astronomy. And photographic plates were in use for a century, from the 1800s all the way through up to 1970s. One additional thing about quantum efficiency is it's also wavelength dependent, and so oftentimes we can also refer to the spectral sensitivity of a detector, and that's the quantum efficiency versus wavelength. So CCDs are really everything astronomers could have ever hoped for in terms of sensitivity. All the photons coming in counted, most of them anyway, and thus we can see things fainter. And then there's a second key property, which I briefly alluded to earlier, which is their linearity. We count photons that get converted into electrons, and it's always proportional up to the saturation limit. The output response of the CCD, aka the voltage of a pixel that's being read out, is directly proportional to the number of photons hitting it. The response is extremely linear to within a fraction of a percent over most of the output range of the digital camera. So this is an example, and we've calibrated this in the lab, so we know this to be true. This is the second key property of digital cameras. It allows us to precisely measure the brightnesses of things. And so this is a chart showing the counts on the y-axis as a function of exposure time, the x-axis, for something that's uniformly bright. So we're watching how bright it is. The longer we expose, the amount of photons it's emitting doesn't change. In this case, it's milliseconds here on the x-axis, but this is a pretty bright source, probably a lamp in the lab or something like that. And so the number of photons that we're getting as a function of time goes up linearly, and the amount of electrons that we're counting goes up linearly as well. So this proportionality is incredibly important to astronomy. And up until about I would say the late 90s, digital cameras had advanced to the point where we could measure the brightnesses of things in the sky to the nearest 1%. This was big. This changed astronomy in a big way, because prior to the invention of the digital camera, we used photographic plates. And emulsion technology is not that great way of measuring brightnesses of things. And until the invention of the digital camera, we were able to measure the brightnesses of things to the nearest 10 to 20%. Like, we could tell something was 5 times brighter than something else, but we couldn't tell that something was 2% brighter than something else. And now we can. And so this was a big deal for our ability to quantify the brightnesses of things in astronomy, and led to the revolution, of course, which is the field I'm involved in, with the discovery of exoplanets. The record holder today in measuring the relative change, the absolute change of brightness is still limited by the Earth's atmosphere, and we can get to about 1% absolute brightness. But in terms of the relative brightnesses of things, the record holder now is actually 150 parts per million from the ground, and 10 parts per million in space. So with digital cameras in space, with the Kepler mission, we've been able to measure the relative changes in brightnesses of stars to the nearest 10 parts per million. I'll let that sink in for a little bit. And the types of science that enables are just absolutely tremendous. It's been a revolution since the launch of Kepler. Kepler broke through the kind of 100 parts per million, I'd say the 1,000 parts per million barrier in great fashion. There's a lot of stellar astrophysics that's enabled as well. So that's kind of the second major reason why astronomers love digital cameras. So let's put it all together. What information do you get when you take an image with an array of pixels in the CCD? As a reminder, the CCD is placed at the focal plane of the telescope, where all the starlight comes to a focus and you can make an image of the sky. We haven't talked about telescopes yet, but we will, and how they work later. So we can imagine displaying the counts. So remember, it's not a color image, it's a monochrome image. And this is imagining if we turned it into a 3D plot here, where the X and Y on the bottom here refer to the X and Y pixel coordinate numbers. And the vertical axis here is the number of counts or intensity of the brightness. And so this is an example of three-dimensional representation. You'll see some 2D representations in class where you're looking down on it from above. But where there's a star, you have an increase in the number of counts, and so we have several stars in this image of varying brightness. And then we have this kind of wavy, kind of rippled background from which the stars emerge at lower count values. And this is, of course, the sky. The sky is not perfectly dark. The sky actually emits light as well. But there's more to it than that. There's also the properties of the detector itself. And we're going to talk about how the detector contributes what's called a bias level, a dark current, and a flat field, one at a time. So the image obtained from a CCD is like several layers of layers of information. The base layer is the noise you get when you run electricity through the chip or through an amplifier. This is called the bias level. You get this regardless of how long the exposure time is. Even an image with length exposure time of 0 has this component. So it's oftentimes called a bias current or a bias voltage, but generally it's the voltage you would measure with everything turned on but not collecting any photons. Then on top of this, there's the hum of the electronics, and this is called the dark current. This is something that accumulates with time. It's a constant rate, often measured in counts per second, and so the longer you expose, the more counts you get. So to account for this, we have to take images with our digital camera without opening the shutter, the thing that lets the light in. Oftentimes it's a digital shutter, but that's immaterial for the purposes of this course. But we have to take images without opening the shutter to account for the hum of the electronics and the bias level. Now, where does the dark current come from? This is the next key difference between the digital cameras in our cell phones and the digital cameras in astronomy. Well, pixels have temperature. And what is temperature? Temperature is the random motion of the particles in a material. And so the hotter the material, the more those particles are moving around. And they're bumping into each other. They're often in a lattice, right, because it's a solid. Well, this thermal movement of atoms can randomly and predictably free up electrons on its own. And that's basically what dark current is. Dark current is the random probability that any given atom, silicon, will randomly free up an electron in that pixel into the valence band. And this happens at a predictable rate, hence the dark current, measured in counts per second. And all digital cameras have this, so what do we do with them? Key point number 3, and the differences between astronomy digital cameras and your cell phone digital cameras, we chill, we make them cold, we cool them down. And so the state-of-the-art digital cameras in the visible and near-infrared, and particularly in the mid-infrared, are cooled down to liquid nitrogen temperatures, just roughly 70 degrees above absolute zero. And this is pretty important. When you go into further wavelengths in the infrared, you have to go to space, and those cameras can be made even smaller with liquid helium. Even colder, not smaller, with liquid helium. But generally speaking, the colder your detector, the less the silicon atoms are bouncing around, and thus the smaller the dark current. And the smaller the dark current, the more sensitive we are to fainter things. Because imagine if you're trying to count individual electrons from something that's very faint, and those electrons are only coming in every so often, but you have the electrons popping out all the time because the atoms are bumping into each other. Well, then you're not going to be able to see the very faint thing. So by making the atoms more still, you can still see the faint thing, and only every once in a while is a random electron going to be kicked out of the atom. So digital cameras in astronomy are often cooled. Now, in our digital camera that we use on the campus telescope, it's kept at a temperature of -20 Celsius, which is not as cold as liquid nitrogen. Unfortunately, we don't have a liquid nitrogen camera. Maybe someday we will. We just got a doer for one in my lab, but we don't have the sensor in there yet. Finally, after you account for the hum of the electronics, this random electrons kicking out, and then the bias voltage that's applied, you also have pixel-to-pixel sensitivity variations. Not all pixels are identical, and this is something that's often masked over in your digital camera cell phones, but it's something we care very much about in astronomy. So some CCD pixels will accumulate light easier than others. This could be caused for a variety of reasons. It could be because the pixel is misshapen or it has a defect. So you can imagine a large pixel is going to collect more photons than a smaller pixel. Or you could have a speck of dust, in front of the camera, on the window to the camera, and that casts a shadow on a set of pixels. And that causes problems, because let's imagine we have a star on a pixel that accumulates photons easily. And then we have another star hitting light on a pixel that doesn't accumulate photons easily. Then we're going to think, let's say they're the same brightness in real life, then we're going to think that this star is actually brighter than this star, when in fact they're the same brightness. So we have to correct for this effect. And that's a process in astronomy called flat fielding. To correct for this, we expose all pixels to the same amount of light, hence the word flat. And they're literally pictures of nothing, a blank screen, a bulb shining in the dome, or a blank piece of the sky. So there are different kinds of flats you can take. So long story short, we take flat fields to divide out the individualized nature of every individual pixel and to make them all equal to each other. The next layer to talk about of information contained in a digital image is the light from the sky itself. Whenever you take an image in astronomy, there's always light that makes its way into your detector. Just like starlight, it contributes to your signal. However, unlike starlight, it should be evenly distributed across your image. Now, of course, the TESS mission, for example, had stray light from Mars in one of its recent sectors. The light was spilling over and reflecting off of part of the side of the camera into the digital, into the other pixels in the field of view. So in any event, unlike starlight, it should be evenly spread across your image. So if we examine pixels that do not have stars or galaxies in them, then we can determine the amount of sky or stray light in our image. You may not realize this, but the night sky is not dark. Now, of course, we're in DC, so there's a lot of light pollution. But even in the most remote locations for astronomical observing, where many of the world's professional observatories are located, the sky glows. There is still light scattering around in the Earth's atmosphere, and they still contribute counts to every pixel in our image. So we have to account for that as well. So those are the different layers that go into making an image of the star. We have the electronics contributing bias voltages, as well as a dark current from the temperature of the material, the silicon. Then we have to correct for the individualized nature of individual pixels. And then we have light from the sky itself, where our objects are not located. And finally, sitting on top of all of that is the light of the things that we are looking at and are interested in, the light of stars or galaxies or otherwise. So that is the end of today's lecture, and I'll see you next week.